Alright, welcome back to week 3, class 2 for Engineering 250. Um, several things to go over today. First of all, I want to talk about NANDs and NOR gates and a special property of these gates. Then I want to talk about compressing truth tables, which we've actually already done in one form. I want to talk about programmable logic, and then conclude by talking about some real world considerations of chips, how chips behave in reality versus how they behave on paper, and how we can analyze the behavior of chips to understand what they actually do in practice. And that's going to lead us into our next unit for the course, which we'll be looking at circuits with memory. So let me begin by discussing a property of NAND and NOR gates. Let's talk about NORs. So remember, a NOR gate looks like an OR, but we complement the output. So an OR gate would have 1 in all of these spots except the first. A NOR gate has zeros in all of these spots except the first. So that's what a NOR does. But there's some interesting properties of this. One thing we can notice about a NOR is that if we set, for example, B to be a 1, and we only look at these two entries in our truth table, the NOR is exactly the same value as the input A. But if we set the B input to be a 0, which is these two rows, the value of the NOR is the opposite of the value of A. So that leads us to a kind of useful little fact. If we have a NOR gate and we set one input to ground and we put another input A in, what we get out is the complement of A. Right? We get the inverse of A. So this NOR gate can actually act like a simple inverter. And if for some reason we didn't have an inverter, we could get this same behavior by using a NOR gate. So NORs let us also do NOTs. So there's an identity from earlier in the course called De Morgan's theorem. And this is a really important identity. You're going to bump across this again and again in this course. Other engineering courses, if you do CS, it'll bump up against it in CSE 215, discrete structures. We'll do it in programming courses. De Morgan's theorem is this cool property that if you take two things and NAND them, you get the same thing as if you OR their complements. And if you take two things and you NOR them, you get the same thing as ANDing their complements. So that's De Morgan's theorem. And it basically says if I want to break up this bar, so instead of putting a bar over the whole expression A and B, I want to put a bar over just A and B, my AND changes to an OR, and vice versa. Or if I want to change from an AND to an OR, I can do that by splitting this complement. So instead of complementing the entire product, I complement each term of the sum. So this is De Morgan's theorem. There's two versions of it, that one and that one. Well, with this NOR gate, we know that we can take two inputs, A and B, and we can generate a NOR. But we also know how to use a NOR gate to get an inverse. I could take this output, put it into a NOR gate, put this input into ground, and whereas this is A NOR B, this is going to be A or B. So from a NOR gate, I can get an inverse, but I can also get a plain old OR gate. So this one NOR gate actually lets me get three different behaviors: NOR, OR, NOT. De Morgan's theorem lets me get even more. So if I have the ability to get a NOR gate, right, I have A, B, and I put that into my NOR. Here's A or B bar. Well, that's the same thing as A bar ANDed with B bar. So if I were to complement my two inputs to a NOR gate, I would get out not A NORed with not B, and that would be the same thing as not A ANDed with not B, which is just A ANDed with B. So I can create an AND gate by doing the following. I can take A, put it through a NOR gate with one input connected to ground, put B into another NOR gate with one input to ground. This gives me A bar, B bar. I can NOR those, and this will be A bar or B bar bar. And De Morgan's theorem says that's the same thing as taking the complement of this, and ANDing them. So that's A bar bar ANDed with B bar bar. And we know that not A is just A, and not B is just B. And so this circuit does the same thing as a simple AND gate. So from a NOR gate, I can get an inverter, I can get a NOR obviously, I can get an OR, I can get an AND, and if I run this through one more inverter, I can get a NAND. So all of my basic building blocks, AND, OR, NAND, NOR, NOT, I can get from a NOR gate. So we say that NOR is a universal gate in the sense that we can build other gates from it. Now, this is certainly more complex than just using an AND gate. But theoretically, we can get the behavior of an AND out of 3 NOR gates. And the same thing happens with NAND gates. If we start with a NAND gate, we can use NANDs to build NORs, ANDs, ORs, and NOTs. And it's kind of a dual process. The inverse comes from NANDing with a 1. And so we can redevelop this. So NANDs and NORs are universal building blocks. An AND is not. There's no way to get an inverse out of an AND, which means we can't get a NAND out of an AND. But NANDs and NORs, they're universal building blocks. And so that's maybe kind of interesting, but it's actually has been a useful characteristic in the past. So in the 1960s, when the United States decided they were going to travel to the moon, land, have somebody walk on it, bring them back safely, John F. Kennedy's national directive, there was the question of how do you build a control system for the spacecraft involved. How do you make systems to control the navigation and monitor fuel and all that kind of stuff. And computers were a thing, but they were a new thing. Computers were generally these big room-sized monstrosities. And the question was, how are we going to implement a computer system? And they decided to use a relatively new technology called an integrated circuit, right? These little chips that we use all the time, the things we talked about in the last class that we look at data sheets for. Well, those didn't really exist in the mainstream in the 1960s. They'd been developed, the previous decade, but they were largely experimental, they were expensive, and they were mostly custom made. So the government decided to hire a place called Lincoln Labs, part of MIT, to manufacture the chips they would need to build the control system for the Apollo guidance computer and other pieces of the spacecraft. And you can find online the schematics for this is the logic flow module for the AGC, the Apollo guidance computer. The thing I want you to note here is that all of these gates, they're NOR gates, right? And this is because they only wanted to manufacture a single type of integrated circuit. Now today, you can go into a parts bin in the collaboratorium and open a box for $250 and you'll see, dozens of different types of integrated circuits. But at the time, these had to be manufactured, and so they said, we're just going to manufacture NOR gates. And we're going to use NOR gates for everything. And so these are all the same type of integrated circuit, and they're doing these things that we just saw we can do using the universality of of a NOR gate to create different types of logic gates. And you'll also find in other parts of the schematic these cross-coupled NOR gates, which we're going to talk about in the next class. These are memory elements, and we'll actually work out the design for a memory element using NOR gates, but we can also do it using NAND gates. And so they built everything out of these single types of gates. So NORs really are universal, and you know, beyond being theoretically interesting, sometimes that's been a practically useful characteristic. All right. Well, along the lines of sort of universal building blocks, there's this notion of programmable logic. The idea of a single physical piece of hardware that can be customized to do different tasks. And we've already encountered a key idea behind this when we looked at how to draw circuit diagrams neatly without a lot of crossed wires. So suppose I wanted to implement a function like f equals ab or b bar c. So what was our trick? We take our inputs, we run them vertically down the page, and next to each one we take that input, put it through an inverter, and run that next to the uninverted signal. So now we have A bar, B bar, C bar. And then we look at the building blocks that we're after. We need to take A and B and AND them together, so we'll make an AND gate, and we'll connect one input to A, and we'll connect one input to B. And then here we need another and we want to use B bar, so we connect an input to B bar, and we want to use C, connect an input to C. And then we take these, and we put them through an OR gate, and there's our output function f. All right, so that's a very mechanical process to build this circuit diagram. Suppose we decided what we really wanted was A bar B or B bar C. Now, if I had done this on pencil, right, with a pencil, all I have to do to get this new circuit is, instead of connecting this horizontal line to A, connect it to A bar. Nothing else in the circuit changes. So this leads to the idea of, what if we had a piece of circuitry that internally had something like, you know, a set of inputs, their complemented values running horizontally, and then a bunch of AND gates with wires running, these are vertical, a bunch of wires running horizontally, and a bunch of output of those connected to OR gates. And what if we could somehow control which of these horizontal lines were connected to which of these vertical lines? And it turns out we can do that. The way we do it is by, the way it was originally done was by using fuses. So if you've lived in an older building, you know that fuses are these things in your electrical system that are there to protect the wires and the walls basically from overheating. If you run too much current through a fuse, the fuse blows. The lights go out, you have to find replacement fuses, go down to the fuse box, put a new fuse in. So a fuse is just a little piece of metal that if you run too much current through it, it'll melt. So imagine a system like this. We have our usual set of inputs. We have some AND gates. We have 3 wires going to each of these AND gates, and so on. And we have a little fuse connecting each of these junctions. So every one of these junctions has a fuse, and so on. And now we have the option of going into this device somehow and picking individual fuses and saying, I want to run a bunch of current through that for just a moment. And we run enough current through to break this connection. And so if we want this input to be connected to A bar, we program the device by running current through in such a way that we destroy all of these connections. And now the only thing feeding this input line is A bar. And if we want this input to come from C, we run current through to destroy all of these connections except this one, which is connected to C. And so we program our device in this way, and we basically choose which of these inputs or their inverses are connected to the inputs of these AND gates. And then we can also take these AND gate outputs and run them through OR gates. And we can make another programmable plane. So we can choose which of these 5 AND outputs are going to get ORed together to generate some function output. And we can have multiple OR gates, each with multiple lines coming in. And so we can create a device with hundreds of fuses in it. And when we get this device, we design our circuit, we decide what equations we want to implement. And then with the help of a computer, we program this device one time by going through and blowing some of the fuses. And when we take the chip out of the programmer, it is hardwired to perform whatever functions we've programmed it to perform. So this is the essence of programmable logic. So when we work with programmable logic, we'll see drawings such as this, where we show our gates with a single input instead of multiple inputs. Now, I've got 3 lines coming in as inputs running vertically and 3 inverses, so I'd probably want 3 inputs to the AND gate. But for the sake of drawing this as what we call a fuse map, right, a way to see which connections are being made, we just show a single input to this, and we understand that if we put a mark here and here and here, then this is going to one of our inputs, this is going to another of our inputs, this is going to another of our inputs. We never draw this when we're making a schematic diagram. We never ever just use a single line. This is only for programmable logic. Same thing over here in what's called the OR plane. We have a set of OR gates. We might have, up to 8 inputs coming from these 8 AND gates going into this OR gate, but we only draw one wire, and we just put a mark wherever we want an output of an AND gate to be connected to an input of an OR gate. So the book takes you through some examples of this, and we'll do some practice problems on this. But this is the idea of programmable logic. And there's 3 main types of programmable logic. This one that we're describing right now, this is called PLA. So this area over here, this is called the AND plane. And this area is called the OR plane. Right, because here you're controlling connections to AND gates, here you're controlling connections to OR gates. So a PLA, the AND plane is programmable, and the OR plane is programmable. So it's completely general. There's a second type of device called a PAL, or a PAL, and in this one the AND plane is programmable, the OR plane is fixed. So we can't change which outputs of AND gates go into OR gates. This is hardwired at the factory, but we can change what's over here, what's being fed into the AND gates. And there's a third type of device called a PROM, and in a PROM the AND plane is fixed, the OR plane is programmable. And so let's look at PROMs for a minute. So let me just stick with 3 inputs. Normally we would have more than 3 inputs to make these things, more useful. But to simplify our drawing, let's just have 3 inputs. And then we're going to have some OR gates. And again, I'm just going to show a single line going into each OR gate. And if I want an output of one of these AND gates to be connected to an input of the OR gate, I'll just put a little mark here to indicate there's a connection. So with a PROM, the feeding of these inputs and their complements into these AND gates is fixed at the factory. So what's a useful way to fix this? Should we make this one take A and B, and this one takes B and C, and this one takes A and C? Well, here's a pretty straightforward approach. Let's have this first gate generate A bar, B bar, C bar. And let's have this second gate generate A bar, B bar, C. And let's have this third gate generate A bar, B, C bar. And let's have this fourth gate generate A bar, B, C. So what are we generating? We're generating minterms. Right, and this last AND gate would be driven by A, ANDed with B, ANDed with C. Well, if I have 8 AND gates here and each one is generating a minterm, we know that we can represent any function of 3 input variables. Because we can write, a function as a compact sum of, a set of minterms. We could say, my function to be F3 plus F4 plus F7. Well, all I got to do is put a connection here at F3, and M3, one at M4, and one at M7. And here's M3 or M4 or M7. So that's what a PROM looks like. A PROM is also interesting because normally when we talk about PROMs, we're not talking about programmable logic. We're talking about memories, programmable read-only memories. So if you look inside the motherboard for a pretty old PC, sometimes you would find a little chip inside. And that chip stored the BIOS, the code that's run when your machine boots up. And it came in a little package with a little quartz window on the top, usually with something covering it. And that was a programmable memory. And how does this work as a memory? Well, let me add one more OR gate. If I want to store 8 4-bit numbers, I can do that in this device. I can think of this as specifying an address, and at each address I can store a 0 or a 1. So for example, if I want to store at location 0 the number 1010, and at location 1 I want to store the number 0111, I would simply set my fuses like this. And now if I input a 0, if I make A, B, and C low, well, this is going to generate a 1, and that 1 is going to feed into this OR gate and this OR gate. It's not going to feed into these two, so the output of my 4 functions here will be 1010. Well, that's the number I stored in location 0. If I set my inputs to 0, 0, 1, that's going to drive this term A bar, B bar, C high, and that 1 is going to feed the OR gates here, here, and here, but not here. So this will output a 0, these will output 1s. My 4-bit output from my chip will be 0, 1, 1, 1. Well, that's the value that I said I wanted to store at location 1. So I can use this to store arbitrary data. And with this particular configuration, I could have 8 locations, and in each of those I could store a separate 4-bit number. And I simply store those numbers by making connections in this OR plane. So parting thought on PROMs, right? PROMs are both a way to encode general purpose logic, but also a way to encode binary data. And so this is a hint that there is some sort of connection between code and data, between something that performs some function and a simple set of information that we store somewhere. And that's a deep subject way off on its own that, you know, I could give you a few days worth of lecture on, because it's been a research area of mine for a number of decades. But that's just something to think about, the connection between logic circuits and just storing information. All right, so if you go to engrcs.com and go to component specifications, down here at the bottom, under medium scale integrated components, you can find a PAL 16L8. And this is an example of programmable logic. It's an inexpensive chip. You can buy this and you can program it. And it comes with a picture of the fuse map. And basically you have multiple inputs, and each input is sent either to one of these horizontal lines as it is, or is inverted and sent to a vertical line, not horizontal, vertical. And so these vertical lines correspond to the inputs, and then here's that, you know, single line showing a connection to an AND gate. And it turns out for each of these, all of the AND gate outputs are ORed together to generate an output, and that output gets inverted on the way out, goes through one final inverter. It also has the ability for most of these cases to feed back into the circuit, both true and inverted, and become an input for itself or for another series of AND gates. So this is a very, very general purpose device. This device right here is called a tri-state output, and it's a way to electrically disconnect this output from pin 19 in this case. If we put a 1 into the side of this triangle, this acts like an inverter. But if we put a 0 on this wire going into the side, it's as if this device did not exist. It's as if there's an open wire between here and pin 19. And so pin 19 is not connected to anything effectively inside the chip. So we can use some of these pins as pure inputs by not driving a voltage onto that pin by turning off these tri-state outputs. So this is a complex device, right? It's got over 2,000 fuses inside it, and if we look at the pinout, you can see it's got, you know, a number of dedicated inputs, a number of lines that can be inputs or outputs, a global output enable pin, and so on. So you know, these are real devices. You can program them and use them. They've been superseded by something called field programmable gate arrays, and we'll talk a little bit about FPGAs towards the end of the course when we get into Verilog. But those seem to be what most engineers go for these days instead of programmable logic. They're just a lot more powerful and not terribly more expensive. All right, so last topic for today is looking at real-world behavior of components. And so let me draw a circuit here. Let's have a single input A, and let's go into an OR gate, and we'll call our output X. And I'm also going to take A and run it through an inverter. And we can ask, you know, how does this circuit behave? So let me label the output of this inverter B, and let's see what X does. So A is either a 0 or a 1. Well, if A is a 0, the input of the inverter is a 0, B is a 1. And so the OR gate always ORs A with B, while 0 ORed with 1 is 1. And if A is a 1, it doesn't really matter what comes in here. If you put a 1 into an OR gate, you're going to get an output of 1. But just for completeness, if A is a 1, B is a 0. But again, 1 ORed with 0 is a 1. So the output of this circuit should always be 1, regardless of whether A is high or low. Well, we can build this circuit. So this is, a proto board. There's an inverter, there's an AND gate, and we've got, power and ground hooked up, and we've got this input coming into pin 1, and it goes directly into an OR gate, but also the inverted signal goes into the OR gate. And then we can measure the output of this along with the input on an oscilloscope. So we played with oscilloscopes in Tinkercad. They let us look at how signals change over time. And we would expect that as we run this, if the input A changes, the output would just stay high. But that's not exactly what happens. What actually happens is when the input goes from 0 to 1, we see a little bit of a blip in the output. Right now the output should always be 5 volts. It's actually 4 volts, and it blips up about 0.4 volts, so up to about 4.4. But when the input drops from 5 volts to 0 volts, we see this. A little line appears here where the input appears to drop down pretty close to 0 volts very, very briefly. So this is 25 microseconds from here to here. That's a long amount of time for a circuit. So we can blow this up, and so here we're just looking at more oscillations of the input, and we can see this behavior where the output drops temporarily. If we blow that up, we can make 25 nanoseconds. So this is 1,000 times the resolution of that first graph. And you can see what's happening. The input goes from high to low, and as that happens, the output drops from 4 volts all the way down to 0 and then comes back up. And it takes it a little bit of time. So we can zoom in 5x more. So here's 5 nanoseconds, 5 billionths of a second from here to here. That's the amount of time it takes basically for electricity to travel about 5 feet. So one of these marks from here to here, that's how long it takes electricity to go, 12 inches. So this is a pretty fine resolution. So here's the input, and it's dropping from 1 to a 0. And you notice it doesn't drop right away. It doesn't go boom. It tapers off. And when it gets down to 0, it doesn't actually stay at 0. It goes up a little and comes down. It oscillates. These are some of the real-world behaviors of electric circuits. So inputs don't change instantaneously from 0 to a 1. They gradually increase, or they gradually decrease from 1 to 0. So we can see that here, but we can see the output as the input begins to drop. The output stays basically a logic 1 for a while, and then it starts to drop off. And at this point, it's definitely a logic 0. And, between here and here is 5 nanoseconds. Between here and here is about 12.5 nanoseconds, during which the output is below 2 volts. And that's probably a logic 0. So, 10, 12 nanoseconds, our circuit is outputting a logic 0, even though it's always supposed to output a logic 1. All right, so this is called a glitch. This is a undesirable behavior of our circuit that's not predicted by this theoretical truth table. But it is there. This does actually happen. We can see it by actually building the circuit. So why is this happening? Well, if we go back to our component specifications, let's take a look at an inverter, and let's take a look at an OR gate. And we've looked at this before, but perhaps with newer eyes this time. So an inverter, input is high, output is low, input's low, output's high. But if we come down here to the electrical characteristics, or the switching characteristics, we can see that there's a propagation delay. And to change from low to high can take up to 22 nanoseconds. to change from high to low. So that's time propagation high-low. So that's going from an output of 1 to 0, can take up to 15 nanoseconds. And typical is 8 to 12. So, ballpark 10, possibly depending on which way we're changing, as bad as 22 nanoseconds. And if we look at the OR gate, and we look at the switching characteristics there, quicker switching, right? Minimum of 4 nanoseconds, maximum of 15. So still, ballpark 10 nanoseconds, definitely within the realm of what kind of time we might see. And this varies from device to device. So these are 74LS, 74S, 7404. There's different kinds of 7404 devices. Anything that's a 7404 is a hex inverter, but there's different technologies. This is a low power device which has different switching characteristics from this, which is a TTL device, or this, which is a Schottky device. You can find versions of chips using what's called emitter coupled logic, ECL, very, very fast, but very power hungry. And these are the circuits that if you build them, you have to cool them with something like Freon or liquid nitrogen. All right, so let's analyze this circuit given that there's a propagation delay. So if A is 0, B is 1, our OR gate says, hey, I see a 1, my output's 1. All right, when we raise our input to 1, the first thing that happens is this OR gate sees a pair of 1s. And it's happy. It's like, oh yeah, I'm outputting a 1, And then 10 nanoseconds later, this 1 goes through the inverter and this becomes a 0. And the OR gate is like, well, I've still got one input that's a 1. I'm going to leave my output as a 1. So that's a solid 1 in that case. All right, but now let's change the input from a 1 to a 0. And the first thing that happens, that 0 travels along this wire very quickly, and the OR gate is seeing a pair of zeros. And it's saying, oh, I got some work to do. I've got to change my output to a 0. So it starts generating a low output, and a few nanoseconds later, that appears. 10 nanoseconds later, this 0 going into our inverter has come out of the inverter as a 1, and now the OR gate says, hey, I've got a 1 that's an input. I should set my output to a 1, and 10 nanoseconds later, it goes ahead and sets the output to a 1. That's where the glitch occurs, right? Because for a brief moment, both of the inputs here are 0, and that's why the OR gate outputs a 0. All right, so it's helpful to be able to analyze these kinds of situations, and we can do that by using what's called a timing diagram. And a timing diagram basically is like what you see on an oscilloscope, but we draw it ourselves. So we have time running in this direction, and let me redraw our circuit. So this goes into an OR gate. Here's our output X. A goes through an inverter. We'll call the output of the inverter B. And let's see what this does. So let me put some time marks on here. And let's suppose that the propagation delay is 10 nanoseconds for both the inverter and the OR gate. And let's suppose that this distance is 5 nanoseconds. All right, so here's our signal A. We're going to start with our signal being low. And then I'm going to make the signal high. And I'm going to leave it high for a bunch of time, and then I'm going to drop it low. All right, so let's draw a picture of what happens to this signal B right here, the output of the OR gate. So B is going to start off high. And if you just see a line, we can't tell if that's high or low. So sometimes we'll draw a little dotted line in the beginning to say, hey, this is low. So let me draw a dotted line here and say, hey, B is high. Okay, at this point the input of the inverter goes goes high, which means B is going to go low, but it doesn't go low right away. It takes 5-10 nanoseconds, and then it goes low. And at this point, the input to the inverter goes low. B is going to go high, but it's going to take 5-10 nanoseconds. And now let's look at our signal X. Well, two inputs, one is low, one is high, so X is going to start off high right here. At this point, A also goes high, so now our inputs are 1 and 1. X is going to stay high. At this point, B goes low. Well, we're still going to have a 1 and a 1, so a 1 and a 0, so X is going to stay high. At this point, A drops low and B is still low. So right here, we've got a pair of zeros going into an OR gate. 0 on A and a 0 on B. So 10 nanoseconds later, the OR gate's going to output a 0. At this point, though, B has gone high, so now we've got a 0 and a 1 going into our OR gate. And so 10 nanoseconds later, the OR gate will correctly respond to that 0, 1 and make an output that's high. So what do we observe here? We observe that for 10 nanoseconds, our output X was low. That's a glitch. Right? Because theoretically, our output should be high in all circumstances, but there is in fact a period of time during which our output is low. That's not predicted by the truth table, but we can see it very clearly with a timing diagram. And so this is an example of the real world behavior of components, right? Things don't change instantaneously, things don't respond instantaneously, and that does more than simply create a delay. Sometimes that can create glitches, right? Undesirable, unexpected changes in output that are different from what the truth table tells us. And so timing diagrams are going to be a useful tool for analyzing the behavior of circuits like this and for identifying things like glitches. So we're going to do a lot of work with drawing timing diagrams, and it takes practice, and it's really a good area where you want to work on graph paper. You'd like to have a straight edge so you can draw, timing marks, draw horizontal lines that are neat, because we might have several signals along here, and work very methodically. Work with a pencil and a good eraser so we can make corrections, and so on and so forth. This is going to be a really, really useful tool for us. All right, so in the next lecture, we're going to extend this idea that circuits take time to respond, and we're going to use that to our advantage. And we're going to introduce a fundamentally new type of circuit, which we call a sequential circuit. And this is going to end up being the building block of what we call state machines. So basically simple computers. All right, thanks. See you next time.